Smith. So he's a geological engineer and hydrogeologist with more than 33 years of experience in soil and ground remediation, stable isotope evaluation, environmental forensics, electrokinetics, and remediation of industrial facilities. Mr. Gregg has been a guest lecturer on the topics of in situ thermal treatment and use of this compound specific isotope analysis, CSIA, at UIC Chicago. And then he has also used the CSIA technique at more than 20 locations around the world to aid in situ characterization. He is well known for his pioneering breakthroughs, successfully completing possible the nation's first dense non-aqueous phase liquid cleanup in the groundwater to regulatory limits in 1999. He holds 6 patents for in situ thermal and electrokinetic treatment process, including a low temperature use of electrical resistance heating that significantly reduces time and cost. Also, Gregg has co-authored an encyclopedic dictionary of hydrogeology and authored a chapter on thermal effects in electrochemical remediation technologies for polluted sites, sediments, and groundwater. So now I'll request Mr. Gregg to start his presentation.
Okay. Well, thank you for that introduction. What you may not have picked up on that introduction was that I haven't done any work in the area of earthen tailings ponds for probably about 10 years now. So it was kind of interesting. Well, actually, it was very interesting listening to the previous talk and trying to glean what I can from it as to progress that's been made. And I'm really sorry that I was unable to attend. Anyways, going to talk about the tailings work that I did back, as I said, back around 10 years ago to look at oil sands tailings and stabilizing them using electrokinetic means. So go to the next slide. So I'll give a back outline of the presentation, where we're going to look at the background on, give a background on electrokinetic applications, the application of electrokinetics on expressing water from clays, the application of electrokinetics to consolidate or accelerate the consolidation of tailings, and selected the concept of what we're thinking about of selective treatment to address critical areas such as dam toe creep, and yeah, just basically that. Okay, from what I can tell from listening to your previous presentation, which was probably only about 15 minutes of it, you've covered a lot of these issues, so I won't bore you with going over that twice. Okay, what we're looking at is that we're expressing water from the tailings and addressing 2 of the failure mechanisms, and that is overtopping of the dam and increasing the height of the dam. Expressing water from tailings also has the added benefit of improving or increasing the tailing pond capacity. Okay, the electrokinetic consolidation to the application of a direct current field was first done by Casagrande, but his work is based on some work that goes back 200 years. That is from Royce, who made a presentation in 1807 to the Moscow Academy of Sciences, where he looked at what happens when you apply electricity to water-saturated non-conductive materials, I guess is the best way to put that. The application of an electrical field neutralizes the surface charges and van der Waals forces on clay platelets as well as other non-conducting materials. Water is expressed from tailings and sludges in the order of about 50%. So we get an immediate volume reduction of about 50%. The expressed water can be treated, recycled, or disposed. So next slide. It can be applied in two basic modes. One is the water express mode, and that is because of the neutralization of the charges on solids. This electrolytically raises and lowers pH in the pore water to neutralize the point of zero charge and to precipitate the minerals. Electrostriction forces, the mode of using for electrostriction is that when you apply an electrical field to a water saturated non-conducting material, you let me see. You get a force vector in the direction of the gradient, and the force vector, the force is proportional to the square of the voltage gradient, and this applies to all water saturated dielectric materials. So you can essentially start to squeeze the material. So EK treatments on coal ash, we did this in the laboratory at Dr. Reddy's lab at UIC. And we saw an increase in the bearing capacity after 48 hours lab testing. And but it's not been independently really replicated, at least not to my knowledge. And as I said, it's been about 10 years since I even looked into this material. It can be used, but using electrokinetics in processes such as electroosmosis, you can prevent the migration and leaching of, or at least stabilize the leaching of heavy metals to groundwater. And that's been addressed in EK field testing. And it might also be possible to apply an electrokinetic field to consolidate clay layers while providing electroosmosis to create electrokinetic barriers. So we feel that we generally just scratch the surface of what we can accomplish with the electrokinetics. This is a sample of tailings pond, wet tailings. Its consistency of, well, it feels a lot like latex paint, actually, with some sand in it, but it's got its mixture of water, bitumen, petroleum, and as you can see and guess, probably absolutely no shear strength or bearing capacity. Okay, in 2011, we tested the tailings at the University of Illinois at Chicago. The testing performed at UIC from February to December 2011 on sodium bentonite slurries, mature fine tailings, fresh fine tailings, and fly ash in 2D cells developed for testing of electrokinetic hazardous waste treatment technologies. The testing determined that after approximately 1100 kilopascal hours, so that's multiplying the applied power and measured in the number of hours that this is applied, this resulted in producing a plastic clay. So you take this slimy, something with a paint-like consistency, viscosity, and you're able to generate clay balls, in essence. You can form them into whatever force you want. You don't want to apply too much electrostrictive force. It tends to harden the material and provides no real benefit. You want to keep the application of the electrostriction force to a minimum, just to achieve the requirements, which in this case was 10 kPa of bearing capacity. And I'll show that in another graph, in a graph coming up shortly. So, yeah, I said the force is proportional to the applied voltage gradient. The work was followed up with additional work in Escondido, California, right? Correct. Using AC with a DC offset and mixtures of the material with sand to see whether we could improve upon the process. Better recoveries were observed with DC though, and mixed with sand created a plastic material that hardens within 2 days. We also found too that after it's gone through this electrokinetic processing, it does not rehydrate. It's dry. It does not absorb any further water. It cannot turn back into slime. And one thing that is to quantify this, we looked at the bearing capacity relative to the moisture content, and found that at a variety of moisture contents, the tailings after treatment exceeded the 10 kPa requirement, and it was 83.3% of the samples that did this. So we think that we could bring it up to probably 90% by adjusting during the treatment system and trying to achieve an optimal application of the electrostrictive force. This is one of Krishna's electrokinetic testing cells. The central portion is here is where the tailing sample was located, was subjected to treatment. We've got the graphite rods within water-filled reservoirs. This provides for water cooling to a certain extent, but what it does more than anything else is that it lowers the amount of current that can be transmitted from the anode to the cathode. The water prevents the system from heating up because it minimizes the contact of the solid electrodes to the solids in the clays. So it minimizes the power demand, if you will. So we've got the power supplies, we've got the multimeter, we've got tubes and jars accepting the water that is expressed from the tailings, and collects that so we can measure it and sample it and do some chemical analysis on that. Okay, clay particles in an aqueous solution have a negative charge. Negative charge produces electrostatic surface property known as the double layer, which creates a net abundance of cations in pore space. So we believe with this, looking at this, if we can neutralize the diffuse double layer, which we can do electrokinetically, that the cations could be held up within the tailings, and in that way control the seepage or the leaching, if you will, of the things like heavy metals from that getting into groundwater and surface water and doing damage that way. And I think I've discovered that, discussed that. Okay, this is just to show you conceptually what the diffuse double layer looks like. I won't dwell on that very much. Okay. DLs, when I was working on this project, it really struck me how much we could be learned from working with different engineering fields and science fields, actually. And so working with them on with the electrokinetic phenomena, could see what has already been used. I mean, Casa Grande did it in the 1930s, yet it wasn't really taken, and it really hasn't taken off since then. I was surprised in learning that it was started how long ago, and that there really hadn't been a lot of follow-on. So what we've got is breakdown through hydrolysis at the electrodes, the anodes and the cathodes. This is showing the view of the breakdown of the water that's in the pore spaces during the electrokinetic treatment. So this is courtesy of Terran Corporation. They are doing some work with a process for hazardous waste site cleanup called the lasagna method, where electrokinetic, where our electrodes are inserted much the same way as what we've done here. And so we've got the transmission of the force applied at the anode, moving water towards the cathode. And you can, as I said before, within Krishna's laboratory apparatus, you were able to collect that water and you could analyze the changes that occurred over time with the separation, if you will, of the positive, the cations and the anions. So it provides a means of limiting the leaching potential from the treated slimes. Okay, so our approach would include electroosmosis, which directs the positively charged ions from anode to cathode. That is, the water moves from anode to cathode where it can be collected and pumped from the soil. The electroosmotic flow depends on the soil nature, water content, pH, and ionic type concentration in the pore water. So these are the information that we would need to go back to the testing that we did 10 years ago to try and determine whether the tailings can be treated electrokinetically at a given location. This is a picture of one of the test cells all loaded up. The applied electrical field has just begun. This sample was, this picture was taken after 15 minutes after startup of the treatment system. The water level, which you can see right about here and here, it's essentially the same. You know, clear water. And I believe in this one, the anode is here and the cathode is here. There are marks here from a previous user of this equipment, so that's not bitumen or anything else that is showing up in the test cell. At the bottom of the test cell, I provided for a layer of sand at the bottom of the test cell and a small layer at the electrode reservoirs. So such that if the water is expressed coming out of the compressed tailings, it would be collected in flow under gravity through the tailings undergoing treatment, then could be collected as we could from the as it flowed from this potential here down to this potential, and it could be collected for sampling and chemical analysis. Okay, so that was done on July 15th, 2011. 3 days later, oh no, sorry, 7 days later, which actually is a good determination because we were finding that it only required approximately 6 to 7 days on most samples that we treated, 6 to 7 days of the application or application of power to get sufficient treatment to mold the clay, mold the slimy material, and express the necessary water, getting the water content down into the lower 60 percentile range, lower 60% rather. In this slide here, you can see black material, subvertical. And so the application of the electrical field goes from, in this case, anode to cathode. And the resulting compressive forces are perpendicular to the direction of the electrokinetic field. And so you get accumulation of material in this location here. You get a dark water here. You get accumulation of material here. But what you find is that for a very small electrical cost, you're able to electrically compress the material. And so let's see. This is a scanning electron microscope showing you the material, the slime material, the tailings before electrokinetic treatment. You can see that the tailings platelets are quite random. There doesn't seem to, looks like a little bit of preference there, but throughout it all, there's vertical, there's subvertical, there's flat, there's inclined, all over the place. And this doesn't make for a very strong structure because also that holds in the moisture into the soil, into the tailings pores rather. But this is what happens to the structure after you've applied the electric field. So this orange arrow represents the direction of the applied open field or applied electrical field. And I tried to draw in here basically the orientation of the clay platelets, which you can see there is some variability, of course. I mean, these are minuscule samples, and but I was surprised when I did this at how well this lines up, at least overall in a general sense. You've got this subvertical orientation, and you can see that corresponds pretty much with what you see on this plexiglass plate. So perpendicular to the direction of the applied voltage. So this is the pattern, or at least up here, it was lined up pretty well with the, lined up pretty well with the platelets here, but it of course was not consistent throughout, and neither was that the goal. This graph shows you the bearing capacity in kPa versus moisture content, or actually the other way around, moisture content to kPa to bearing capacity. The cleanup goal was, or not the cleanup goal, the treatment goal was to attain 10 kPa strength bearing capacity. Basically, if it could hold up a pickup truck, and it did for the most part. There's two samples here that didn't quite get to the 10 kPa. Is the 10 kPa represented by this line. So there are 12 samples that we took here. Of those 12 samples, 10 passed the 10 kPa test, and only 2 did not, and that's an achievement of 83.3% of the goal, even though we were really focused on the goal. We could, part of the testing to look at further feasibility would be to determine, how much control do we truly have on hitting 10 kPa. This sample up here this I was just basically done for fun. I wanted to see how hard I could make this material, and essentially a rock. This is a picture of a core of the treated tailings material in these unconfined compressive strength test. And you can see the planes of weaknesses that occurred as you applied the force. So it looks quite plastic, and it is quite plastic, at least for the first few days after treatment. These gentlemen work for Terran Corporation, and they're assembling the electrodes in the field. They're essentially sheet metal ribbons wrapped in geofabric. And the purpose of this is to prevent the contact, solid to solid contact within the groundwater between the sediments and or soil particles in the groundwater versus the electrodes. We didn't want any short circuiting. We didn't want any excess consumption of electrical power. And these geofabrics provide that isolation. So this is talking about electrokinetics, where we're coming from now that we've looked at what the successes that we've had in the field. And what we're looking at is to take the approach that we've learned here, update it, see what other researchers have found, and then start to develop the protocols for looking at feasibility and detailed costing. But what we're relying upon is to look at the electroosmotic field. Can we control the water? So we feel that there was still inconsistencies that we would like to control as for how much water we could get, whether we could get the water to be where we wanted it to be even distribution of water. We didn't want to, we didn't want to have mushy spots in the material. Okay, and to summarize, the electrokinetic fields on water saturated soils were conducted more than 200 years ago. It's not new technology, obviously. The electrokinetic applications on water saturated constituents were essentially thixotropic materials that rendered them useful. We took that thixotropic material, it flows on its own, and we rendered them useful actually for making a construction material, as long as we could get remold them in the time frame before it turned rock hard. And we believe, based on the testing and the costing that we've done to date, it's very, very promising to take this to the next level, to look at feasibility of treating other similar type tailings. You can use a lot of different things for electrodes. One option has even been considered to use a section of chain link fence or steel mesh. Steel mesh has been used in the environmental fields to provide grounding. So it seems to me that it'd be a logical step, if you will, to look at steel mesh as a way to spread the electrical charge and take a chapter from the book on the lasagna method and see if we could use that to apply the electrical field in a more consistent pattern across the application face, and use that then to address areas where there's been toe creep in the tailings or the earthen dams or the tailings dams. Another thought that came up too was to take a network of electrodes, and you're going to see, if it's exposed to the surface, you're going to see some fracturing in the top of the clay. And one of the areas that we looked at was, as these fractures develop, was to take and fill those with bentonite and apply the electrostrictive force to seal these things up in a much better, more consistent manner. And the EK array is powered for 1 to 2 weeks. I've my experience in doing most of the testing at the lab here at UIC. It was typically about a week. We saw as much treatment as was necessary. And also most of the water moisture content was down below 60%, which is the secondary goal for the treatment. What we see as benefits for the EK application is to strengthen and reduce seepage at earth, dam, toe, and foot in the interior face. We feel that this would help immensely for applying it at the interior face because you can mold this material and at least hopefully, we haven't tested it yet, hopefully come up with a material that better prevents the seepage of water from the inside face of the tailings dam. And this way, this would help reduce the potential for dam failure. This would also provide increased measurable safety and service life to the existing geotechnical structure. And it represents significantly less cost and time compared to conventional stabilization options. And with that, I'll be willing to take some questions. As I said, it's been 11 years, so I don't remember all the details. Any questions? Okay.
Professor Das, are you there?
Yes, I am.
Thank
Hello?
you.
Oh, thank you.
So there are 2-3 queries. Will you be interested to take it?
I'm sorry?
So there are some questions. Will you be interested to take it?
I'll try and answer them as best I can. As I said, it's been a while.
Okay. This one has asked Pratik Goel, is this electrokinetic technique can be applied after construction? How settlements are controlled to be permissible limit?
I've never thought of that. I think you could use as part of the construction part. I don't see any reason why not. I mean, we produced a plastic clay. It would seem to me that you could use it as any kind of water barrier. You could make it integral to the construction of, say, a tailings dam. So the construction portion there, yeah, it's worth. I can't think of a reason why. I would say out of hand, no, absolutely not. I think it would be worth running a few tests.
Okay, that's okay. So have you evaluated the relative cost per volume to apply this technology at a pilot or full-scale model?
We did some full-scale modeling. We were looking at cost per cubic meter of around $17 a cubic meter, and that was US dollars. The electricity costs hovered around $5 a cubic meter, and that was inclusive in the 17. So, I mean, it's a construction project, so you may have to move equipment from far away, but we felt that 17 was probably a good gut check number.
Okay. That is one question is there. Can they fly as particles in terms of PZC be expected to high acidic medium near the anode
Yes.
and subsequent formation of inverse electroosmotic flow.
I'm sorry, I didn't quite get that one.
Okay, so I mean, he has asked the question actually not very clear from Dimitri. So
Yeah.
he has asked that recharge of fly ash particles, the PZ in terms of PZC, be expected in high acidic medium near the anode. I think this question is clear. We should not take it. Okay.
Yeah. Yeah.
Yeah. Thank you. Thank you. Thank you very much. Sorry. Actually, it is not very clear. I mean, I'm not
Well,
able to
whoever
get it.
asked that question can, I've got my email address if you want to ask me.
I'll request him. That is, yeah, if Dimitri, so you can do that. So so make it clear and full so that you'll be able to get your answer. Thank you very
Okay.
much, Mr. Greg. So it was too hectic for you, but thank you very much for coming and giving
It was a
this
little bit of
presentation.
stress trying to